Welcome back to Code Meets World. Today we're looking at LeetCode problem number 199, which is the binary tree right side view. To solve this problem, what we need to do is, given any binary tree, we need to return what you would see if you were just looking at the tree from the right-hand side. So if you were looking at the tree from the right, like this, what would you see? If we pretend that a node blocks us from seeing any nodes behind it from a side view, then what we would see from the side is we would see this 6. We would also see this 8, but not the 2, because that's behind the 8. And then we would also see the 7, but not the 4, because these are both behind the nodes on the right. So in this case, the final answer to this problem that we would want to return for this tree is 6, 8, 7. We need to return the right side view starting from the root node and going down as far as it goes. As far as how we might go about solving this, something that comes to mind right away is just going down the right-hand side of the tree and just always going to the right. And that sounds like a good idea at first, but as you notice, this 7 is not the right child, it's the left child. And for a variety of reasons, we can't just iterate down the right-hand side of the tree, because remember, eventually, this 7 might not even be there, and then we would have to return 6, 8, 4. So we can't just always go down the right-hand side of the tree, because one of the nodes we see could actually end up being on the left-hand side of the tree. So what should we do here instead? What comes to mind is a level order traversal, which, if you haven't heard of a level order traversal, that's just where you go and iterate over each level of the tree at a time. And we only process one level completely before we move on to the next level. And we usually use a queue data structure to do that. So what if we did a level order traversal here? And when we get to each level, what we have to ask ourselves is, what is the rightmost element in this level? So of course at the top it would be the 6 because it's the only element there. In the second level it would be the 8. In the third level it would be a 7. So this seems like it would work. And what we have to do here is modify a level order tree traversal to fit this criteria so we can grab the rightmost node at every level. So let's walk through a level order traversal and talk about how we can adapt that to solve this problem. So level order traversals need a queue. And we have the queue so that we can add nodes to it and keep going until we've processed them all. If we were doing a level order traversal here, we would start by inserting the 6 node into the queue, and then starting our loop while the queue is not empty. So the first thing we would usually do in a level order traversal is pop the 6 out of the queue, and then process it, and then add both of its children to the queue. So we would then add 2, and we would add 8. And let's say we also have a solution, which is the array, and we've added 6 to it. So now what usually happens next in a level order traversal is we pop our next value, which is the 2. We process it and say, okay, what children does it have? It has a 4 as its child. So then we add the 4 to the queue. Now at this point, we should stop and say, okay, clearly the level order traversal doesn't work here, because how are we supposed to know which of these values we actually want to add into our solution? When you do a level order traversal of a tree, there's nothing that actually tells us, hey, the node that you're currently at in the queue is the end of the level. All the levels just get blended together. So we need a way to handle that. Here's my proposal for what we should do to handle this. At this point, we should stop and say, okay, we're on a new level. So before we do anything else, let's take whatever the last value was that we added to the queue. So what's at the back of the queue? There's an 8 at the back of the queue. So we should take that 8 and we should add it to our solution. Now, instead of looping over the queue until it's empty, we should say how many values are in the queue. Right now, there are 2 values, meaning we know this level has 2 total values in it. So let's create a for loop that loops exactly 2 times. And what it does is it pops the value off of the queue, so the 2, adds all of its children, which would be 4. Then that was the first run. Remember, we need to run twice because there were 2 nodes on this level. So then we run a second time. We pop the 8, and we add its children, which are 7. And now, because we ran twice, we stop and ask ourselves the same question again, because now the whole next level has definitely been added. So now we ask, what was the last value added to the queue? It was 7. So we go ahead and add that to our solution array. And then we ask ourselves, okay, how many values are in the queue? Again, there's just 2. So let's run a loop twice where we pop 4 and add its children. 4 doesn't have any children, so we don't add anything. And then we pop 7 and add its children. It doesn't have any, so we don't add anything. And at this point, there are no more nodes to process. So we know we've finished, and we can return this as our solution. So we can say if not root, then we can just return an empty list because there is no right side view of an empty tree. If the root is not none, then what we can do is create our solution array, which is what we'll return at the end. And we can also create our queue, and I'm just going to call it the letter Q, and that's going to be a deck in Python, which I've talked about in several of my other videos, and we'll just add the root to that. Now we're going to do the 2 things I talked about on the whiteboard, which is in a normal level order traversal, we would loop over the queue while it exists, meaning while it's not empty. And we would usually pop the first element, do something with it, and then add the children. But remember here, what we're going to do first is say, let's look at the last value that was added to the queue, so the back value, and let's append that to our solution, because we know that'll be the right-hand side of the tree. So to do that, we can say solution.append, and then because a deck is just an array, basically, with access to both sides, the front and the back, if we just say q -1, that'll get the last value in the queue. So we can append q -1, and this is a node, so we have to take its value, and we'll append to that. Then, once we've done that, we need to loop over the queue exactly the amount of times as there are nodes in the queue to make sure we process the whole level. So we can say we just need to run it a certain number of times, so I don't need the I variable, but for underscore in range, and then I guess we can just say length of queue, like so. So if there were 2 elements in the queue, this loop will run twice. And all we simply want to do is say that the current equals q.pop, and then, or maybe it's probably pop left, because -1 will get the rightmost value in the queue. So I want to pop off the front of the queue, which is pop left. So we'll pop the value off, and then we just have to add its children if they exist. So if current.left exists, then we will say q.append current.left, and likewise, if current.right exists, then we will say q.append current.right, like that. And then if I'm not mistaken, we can just return the solution at the end, and hopefully this works. So let's run. Yeah, that looks like it has worked for all 3 test cases. And so now I will submit. And yeah, look at that. That's been accepted. And so hopefully this makes a lot of sense. Let me know down below if you have any questions or comments. I will see you next time.